In this webcast, we'll learn that substituents on a benzene ring can either activate or deactivate that ring toward electrophilic aromatic substitution. Remind yourself of the mechanism of electrophilic aromatic substitution. The first step is the association of electrophile with the pi system, and so the pi system is serving as the nucleophile. Also remember that there's going to be positive charge developing on the benzene ring and a positively charged intermediate along the way before the electrophile dissociation step. So the reaction coordinates diagrams look like this, starting from the starting substrates in which there's either an electron withdrawing group, a hydrogen atom, or an electron donating group on the ring. We see that we'll pass through the rate determining step, the highest point in the reaction energy profile, head to that positively charged intermediate, and then undergo electrophile dissociation onto products. Now, we're looking for the most nucleophilic ring and the ring that's best able to stabilize the developing positive charge in the transition state, leading to that positively charged intermediates. Any substituent that withdraws electron density from the ring is going to make that ring a poorer nucleophile and is going to destabilize that positive charge that's developing in the transition state. This ring is going to be deactivated toward electrophilic aromatic substitution. In contrast, any substituent that donates electron density into the ring is going to make that ring more nucleophilic. It's going to help to stabilize the positive charge that's developing in the transition state and in that intermediate, and it will activate the ring toward electrophilic aromatic substitution. Let's take a look at some actual examples of substituents with electron withdrawing and electron donating groups and the intermediates that appear along this reaction pathway. The carbonyl group of benzaldehyde would be an example of an electron withdrawing group. In the first step of electrophilic aromatic substitution, there's going to be the nucleophilic attack of the pi bond on the electrophile, leading to this positively charged intermediate. We can think about the resonance contributors, and one of those resonance contributors is going to place this positive charge adjacent to this carbonyl group. And remember that the carbonyl group is polarized to be partial plus, partial minus in that direction. And so we have a positive charge adjacent to this partial positive charge of the carbonyl, and that's a destabilizing interaction. Molecules with electron withdrawing groups, like carbonyls, are deactivated towards electrophilic aromatic substitution. What about in the case of this dimethylamino group? In this case, it's an electron donating group, and now we see a very beneficial effect of that substituent in activating the ring toward electrophilic aromatic substitution. In the A sub E step, we generate the positively charged intermediate shown here, and now we can take that pair of electrons and donate it into the ring and create an intermediate that has a complete octet of electrons on every atom. This is a much more stabilized intermediate than the one that we had up here. Because of this, electron donating groups activate the ring toward electrophilic aromatic substitution, while electron withdrawing groups deactivate the ring. Substituents are not only capable of deactivating or activating rings, but they can also influence the direction of regiochemistry in electrophilic aromatic substitutions. And by that, I mean if X is an electron withdrawing or an electron donating substituent, the incoming electrophile could substitute the hydrogen adjacent to that position. That'll make the ortho substitution. Or that electrophile could enter into the meta position, 2 atoms removed from the substituent, or 3 atoms removed from the substituent, the para position. All activating substituents, the electron donating substituents, and the weakly deactivating halogens are known as ortho-para directors. That is, if X is an electron donating substituent or a halogen, the resulting substitution takes place in the ortho position next to the substituent or in the para position opposite of the substituent. In contrast, electron withdrawing substituents, anything that's more deactivating than a halogen, is a meta director. The reason for these preferences can be explained by considering the molecular orbital diagrams or by looking at the resonance contributors, as we did in the previous slide. Let me conclude by giving you a chart which organizes the various substituents according to whether they activate or deactivate rings toward electrophilic aromatic substitution. We're going to use as our standard of comparison the substituent that's a hydrogen atom, and all of the activating substituents, you'll notice, have a pair of electrons on the substituent that can be donated into the ring and activated, until we get down to the weakly activating groups shown here. These are all ortho para directors. Based on that same standard of comparison, anything that's below the hydrogen atom is a deactivating substituent because it's electron withdrawing. These not only deactivate the ring toward electrophilic aromatic substitution, but these are all meta-directors as well once we get below the halogens. In this webcast, we learned that substituents on a benzene ring could either activate or deactivate the ring toward electrophilic aromatic substitution. We also saw how these substituents could direct the incoming electrophile to particular sites within the ring, either the meta position or the ortho and para positions. The kinds of concepts that we used to understand these reactivity trends can also be applied to other substitution pathways like the nucleophilic aromatic substitution pathway.